Hi everyone. This week we are going to continue lecture 3 about forecasting. So this is section 2 of this chapter, and this section will be covered in 3 parts, and this is the first part of the pre-recorded videos. So we are still in chapter 2 of the textbook, or lecture 3 of our course, and it's about forecasting. And in the previous section 1, we had the stationary time series, and in this section we are going to consider time series with trend and seasonality. So in this section, at first, we will have the time series with a trend, and we'll learn 2 methods here, linear regression and Holt's method, which is a double exponential smoothing method. And then we'll consider the time series with seasonality. So we'll see what are the methods for seasonal series and how can we calculate seasonal factors. And then we'll learn how we can decompose a seasonal series, and then we'll learn the winters method, one of the most applicable methods for time series with seasonality. And at the end we'll have some discussions. Okay, in section 1 we had a stationary time series, so we assume that the average of the variable is constant over time, and there's just a fluctuation over time. And then we consider 2 methods over there, moving averages and exponential smoothing. Now we are going to consider the time series with trends. So the time series could be in uptrend or downtrend behavior, and if we see this kind of behavior in our time series, so we can consider linear regression or Holt's method for forecasting. Okay, the first method in time series with trend is linear regression. So here we assume that we have one independent variable, which is x, and one dependent variable, which is y, and that will be the variable that we're going to forecast its value in the future. And so we have n paired data, x and y, so we have n historical data here, and we are going to consider a linear relationship between x and y. So we will estimate a straight line relationship between x and y. Okay, so since it's linear, so we have one intercept, which is a, and its slope, which is b, and we need to estimate the value of these two parameters, intercept and slope, in order to have the function of the straight line. Okay, and in order to estimate the parameters a and b, we are going to minimize the sum of squared distance between the regression line and the data points. Let me show this here. So let's say here is the x and y, and let's say we have these data points here. Okay, these are our data points. Okay, and we're going to estimate this relationship with a straight line. So yeah, let's say this is our straight line, and it's going to be an estimated straight line for those data points. Okay, and so for the errors here, we see, let me show with a different color. Yeah, so this will be the distance, right? These are the distances, are the errors between the estimated value and the data points. So if we calculate these distances as the error of the estimate, and then take the square value of these distances, and then minimize the sum of these squared values, then by doing that we can actually estimate the value of the parameters of a and b in the way that we minimize the sum of squared errors. Okay. So as you know, the linear regression is one of the models which is in the category of causal models, right? Because we can't have independent variables. But here, since we just have a time series data, so we will consider the time as our independent variable. Uh, so so it's not actually a causal model here. Yeah, it's we are actually fitting the linear regression to a time series data. So yeah, the independent variable x becomes t, the time here, and so we are going to make this relationship between t and our data. Okay, so by having the MSE method, minimizing the squared error, we can obtain or estimate the value of the parameters of A and B. And here are the equations to obtain A and B. But yeah, these are the equations. You can easily apply these equations in Excel, but you know that you can use Excel for linear regression. It has a function in data analysis part of Excel. So yeah, you can use that function without going through these equations in Excel. Okay. Here we have an example. We can calculate the parameters A and B by having the sum over di, sum over I times di, and n as 5. So by using the formulas that we had in the previous slide, so we can calculate the value of parameters A and B. If we do this, then we'll have this linear relationship between T and the demand here. So the intercept is 211.4 and the slope is minus 1.4. Okay, so if here we are, as you see here, we are at period 5, right? And if we want to make a forecast for period 8, then what should we do here? We just easily put 8 for t. Yeah, I mean, since here the independent variable is t, so you can consider any value for t as the period, and then you can estimate the demand for that period. So for period 8, by using the linear regression here, we are estimating that demand could be 200.2. Okay, so as a discussion, what if we are now at the end of period 7 and need to forecast period 8? What should we do here? Since we are assuming that here we are at the end of period 7, then we need to recalculate the parameters of A and B. Yeah, actually, as we obtain new data, we need to update the intercept and the slope. So we need to recalculate the values of A and B, and then by having the updated linear regression model, we can apply that for estimating the demand at period 8. Okay. Let's have the second method here, which is the Holt's method, and it's also known as a double exponential smoothing method. So in this method, if we want to make a forecast for tau a step ahead, then it will be this. So as you see here, we have an intercept. ST here is an intercept, and GT is the slope at time t. So if you want to make a forecast for tau step ahead, we will add up the tau times slope with the intercept. Okay, so yeah, this is our model here. So here we assume, since we have trend in our data series, so we need to have an intercept, and also we need to have a slope. Okay, the Holt's method is a double exponential smoothing, and so it has two smoothing constants, alpha and beta here, and two smoothing equations. Okay, one for intercept and the other one for slope. So for this intercept, so the intercept at time t will be a weighted average between the actual demand of that period and the forecast demand of that period. So yeah, the st plus g t minus 1 actually is the f t minus 1. I mean, the forecast that we calculate at time t minus 1 for time t, because here we assume that at st minus 1 plus tau gt minus 1, and tau here is 1. So the st minus 1 plus gt minus 1 will be the forecast. So here we are taking a weighted average by alpha between the actual demand and the forecasted demand as the updated intercept. Okay, and for the slope, actually we use a st, the new st and st minus 1 in order to revise the slope, and then we will consider this revised slope and the previous estimation for the slope gt minus 1, and then again we take a weighted average between these two in order to update the slope at time t. Okay, the smoothing constants alpha and beta could be the same, but more stability can be reached when we have beta less than or equal to alpha. Okay, so here we have an example, and I ask you to try to solve this example by your own, and we will have this example in our live session this week. Okay, so yeah, I'll explain this table in the live session as well. We will also have these discussions in the live session this week. Okay, thank you.